So I'm Giulia Tessari. I'm coming from Switzerland. I'm working for SARMAP, a Swiss company that is dealing with radar data, satellite radar data. And here we are presenting a work that has been running over one of the main landslides that are affecting Uttarakhand state in India. So I'm presenting you what we have done thanks to a project supported by the Swiss Development Cooperation. So Switzerland actually is investing a lot of money on supporting the Indian government and minister with new technologies and trying to integrate what is the expertise from Switzerland with what is the local expertise in India. So just to give an overview of what are the main applications of the technique we are using. So we are speaking about radar data acquired by satellite. And there are plenty of applications where these data are really useful, starting from natural disaster to topography monitoring, land displacement, everything that is related to monitoring infrastructures, agriculture, defense, oil and gas extraction, snow and glacier, landslides. So as you can get, most of them are really important and affecting several areas all around the world, but most of them are also real issues here in India. So just for a fast overview of this data and why it is important to deal with this kind of application, this kind of technology. So SAR data that stay for synthetic aperture radar are data that are acquired in the microwave band of the electromagnetic spectrum. So they are acquiring in different bands. But what is most important is that they are really not sensitive to any cloud cover. So compared to optical data, they can acquire in any day and night condition, and they can acquire even when clouds are there. So you can see from this slide how clouds quite often are affecting optical data, while the corresponding radar data is not at all affected by cloud cover. Here an example of VR flooding in 2017. So you see here some optical data, Sentinel-SAR data, and here the corresponding radar data. So it's really easy to see the importance in most of the case when you are analyzing, for example, flooding or any other disaster that can be induced by weather condition. So a good point of radar data actually is that they can easily get a resolution similar to the one of optical data. As you see from this slide, we have data, radar data up to 0.5 meter resolution. That is really comparable with optical data. And another good point of this data compared to the traditional monitoring system is that they have a good potential in monitoring infrastructure. As you said, for example, say here we have a dam, and to monitor this dam, they are doing some leveling, some GPS measurements, and they are acquiring 200 points every 6 months. Actually, this is really time-consuming, and the information is just punctual, is not spatially distributed. So in case of radar data and any kind of remote sensing data, we have the capability of getting information over very large data area, not just the dam itself. Then we can get information more often, because with this Sentinel data we were using, we can get data every 12 days, up to every 6 days, instead of twice per year. And even more, we are really sensitive to really small deformation, up to few millimeters deformation. So actually, there is a good potential of integrating ground measurement with this kind of remote sensing technique. Another good reason to use this data is that actually a lot of different satellite, different missions are available. So a lot of space agencies all around the world are acquiring this radar data. Now we are focused on this Sentinel data because the European Space Agency is providing data for free. But there are also some Indian missions, so research mission is acquiring over India specifically, and the new mission NISAR, that is a combined mission between NASA and ISRO, is coming in a couple of years, so plenty of data will be available over India. And here, just this slide is just showing how is the coverage, the work coverage of Sentinel data all over the world. So data now are available all over the world, and it's just, you can make sure that any area you are analyzing, you will have data. And we can work, as I was saying, over very large area, and we can have information from different data sets. In this case, Sentinel is acquiring with 2 different acquisition geometry, ascending and descending. And this is helping very much in this case on landslide monitoring. So today we are focused on landslide monitoring, and this gives us the possibility of detect even few millimeter deformation over our landslide. I'm just skipping some too technical stuff, and I'm going to this. Okay, so what is doing this technique is mainly using this radar signal that is sent from the satellite, and the backscatter signal itself is registered from the satellite itself. So the satellite is flying over the same area several times, multiple times, and every time detecting the same target, the same object. If the object in the ground is moving, the satellite is sensitive to this deformation. So the way, the path, the ray that is connecting the satellite and the ground surface is changing, and we are able so to define this dr, delta r, the red part of the path, that is due to the house, in this case of the house subsidence. So again, just to show you what we are measuring and why we are sensitive to few millimeters deformation, we are sensitive to this small fraction of the wavelength. So this small fraction, this red part of our wavelength, that is just few centimeters. So we are really sensitive to few millimeter deformation. Okay, this is a case where these data are largely adapted, used, that is to monitor earthquake. I'm just going to our analysis. So we are here using interferometry. So this radar interferometry is, at the end, just the combination of multiple acquisition of our satellite over the same area. So in this case, you see the satellite is flying over the same area twice, and what we calculate is the phase difference between the two acquisitions. This is giving us these fringes, these colorful fringes that actually can be converted in deformation. Okay, so our main focus now, you will have a lot of information, a lot of equation to solve, but it's not our key point here. From this equation, we are able to extract the movement. So we were using multiple scenes, so we were using a lot of Sentinel data. As I was saying, Sentinel is flying over India every 12 days. And so we have a lot of data starting from 2014. We were using all the available data, and we were using one of the well-known techniques in this field that is called SBAS, small baseline subset. And our aim was to detect the deformation of the slope. So the satellite was able to detect if the slope was moving far from the satellite or toward the satellite. And having two acquisition geometries, so we got two different data sets, one acquired along the ascending direction, one along the descending, and we could get two different, measure the deformation from two different view angle, incidence angle, and combine them to get two velocity, two deformation map, one along the vertical direction and one along the east-west direction. Here are the data we were using. So these Sentinel data, as I was saying, acquired by the European Space Agency, are freely available. The visiting time of the satellite is 12 days. The ground resolution is 15 meters. We were using 105 scenes from March 2015 up to September 2019. So we completed this study really recently. And we were using a second data set acquired with the descending geometry, same characteristic. In this case, we got only 95 scenes over the same period. As a reference digital elevation model, we use the SRTM3. And here is, I go to the case study and to our results. So we were focused on Nainital municipalities. So Nainital is located in Uttarakhand, in the southeastern part of Uttarakhand. And we were using all the available data, as I was mentioning, and this SBAS technique. And so again, because we got two different data sets, we could get the vertical and east-west direction of the formation. This is our final result. So what we get at the end is a velocity map. In this case, is the cumulative displacement map. What you see in blue is something that is subsiding, so it's moving downwards. And the rate of deformation, the total deformation we got was around up to 5 to 6 centimeters in 5 years. So you see we are really sensitive to small deformation. Everything that you see in green is stable. We could also get the horizontal deformation map. In this case, what is blue is moving westward. And even more, what is really great of this technique is that we are not just able to see the average velocity over our area, but we can retrieve the evolution in time of the formation for each pixel that is 15-meter resolution. So here I just selected 4 points. As you see, each point has two different curves, two different plots. One is the horizontal deformation in time, and the second one is the vertical. And you can see easily that we can detect from this time series the evolution in time. So if our landslide, our slope is accelerating or is going on moving with the same rate, if there is a difference between the horizontal and vertical component. In this case, it was really interesting to see some seasonal behavior in the horizontal component of P1. I selected 2 more points. P4, the last plot, is actually stable, so you can see that not everything is moving. We also got stable points. But it was really clear to see how much was moving all the slope located in the northern part of this frame. So this area is actually clearly affected by a landslide, and this information was shared with the Minister of Disaster of Uttarakhand. So they are already monitoring the area, so they are trying to integrate this information and identify what is really moving over the area to define where to set all the ground station, all the ground measurement. And last interesting thing, I was mentioning I saw a strong seasonal behavior, so I went back to search why these oscillations were overlapping the trend of deformation. And I just select 1 point, and here I zoom what I found. I tried to find out the rainfall amount in this area, in Nainital. And actually, the peak of rainfall is always in July here, over here. So you can see here the blue curve corresponds to the monthly rainfall, and the red curve corresponds to the deformation. And you see we have an acceleration every time that we have the peak of rainfall. While when the rainfall is not there, the curve is stable. So the landslides stop and it reactivate every time that the rainfall increases. So this information, I mean, what has been done, and as I was mentioning at the beginning, was supported by the Swiss Development Cooperation, was a sort of demo to see the importance of this technique, remote sensing technique, to be integrated with other measurement, other kind of monitoring system. And all this information are now shared with the local minister that can take advantage of this additional data to integrate with their own system.